Hi, chemistry students. This is your lesson on the law of conservation of matter, sometimes called the law of conservation of mass. All right, so first of all, you're going to be taking some Cornell notes again. The title of your Cornell notes should be the law of conservation of matter, and also you want to have the date. And remember, at the end, you're going to be submitting a summary of your notes. So atoms are tiny and abundant. 500,000 atoms lined up end to end could hide behind a human hair. And so that's width-wise. You could have 500,000 atoms just in the width of this teeny human hair. Atoms are durable, which means they really are very difficult to destroy. Every atom created has been through several stars and millions of organisms. And you see the little cartoon here that says, the girl interrogating an atom here on the chair, saying, where were you on Tuesday 1,000,000 years ago? Talk, because the atom stays around for a very long time. That's because atoms are recycled. It's estimated that 1 billion of the atoms that make us up also belong to Shakespeare or almost any historical figure you can name. Now, it may not be Elvis, because Elvis is only within the last century. He's too recent. But when we die, our atoms may become part of a leaf or a dewdrop or eventually even a new person. The father of the law of conservation of matter or conservation of mass was a man named Antoine Lavoisier. You do not need to know his name, but he was a French nobleman, a tax collector during the French Revolution. He had married a very young woman, only 14 years old when he married her, and they were very rich and they spent a lot of money on doing experiments, and they became fascinated with seeing if they could collect everything that came out of chemical reactions they were doing. And they found essentially that they couldn't ever create or destroy matter, that if they kept everything in a closed system, that matter just transformed. And they came up with this idea of the law of conservation of mass. Now, interestingly, as a nobleman in France, he did not outlive the French Revolution. He was actually eventually beheaded. His wife, Madame Lavoisier, actually did escape before the guillotine was in play in the French Revolution. So she carried on his work and publicized his work even after he passed on. So here is the law of conservation of mass that you should definitely write down in your notes. Mass is neither created nor destroyed in ordinary chemical and physical changes. Must start and end with the same amount. They did a lot of combustion reactions, Lavoisier's, and essentially it was this. You have a log and fire, which is a form of matter, plasma, and burning a log. You keep it in a closed system. You don't let anything escape. You're left at the end with ash and a lot of smoke that you have trapped. You can see that what you start with, which is called the reactants, are what you start with, weighs 31 kilograms. What you end with, which is called the products, also weighs 31 kilograms. Now, here's another example of the law of conservation of mass. In this little flask right here, we have a very small amount of vinegar. In the end of the balloon, there's a small amount of baking soda, and we also have the flask. So the baking soda and vinegar are called the reactants, and nothing has happened yet. You can see the weight from the electronic scale is 3.861 grams. We then invert the balloon, so we mix the two, baking soda and vinegar, and you can see that a gas is formed that we trapped in the balloon. We actually form a salt, water, and carbon dioxide gas, but because this is a closed system, nothing can escape in this chemical reaction. So again, at the end of the reaction, once this is all reacted, and you can see the bubbles are gone here in this last picture, you have the exact same amount of mass. And here's another way to show it in pictures. We've done these particle drawings in the previous lesson, and here is a molecule of the compound CH4, 1 carbon, 4 hydrogens. We have 2 of the diatomic molecular element oxygen, and we are transforming it, changing it chemically, because we have new pictures over here, but the same building blocks. So this is CO2, 1 carbon and 2 oxygen. This is 2 H2O molecules. And again, you can count. We've got 1 carbon, that's the black circle, and 1 carbon, that's the black circle. Reactant side, product side. We have 1, 2, 3, 4 white circles. 1, 2, 3, 4, that's the hydrogen atoms on both sides. And we have 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4 on this side of oxygen, 1, 2, 3, 4 on this side of oxygen atoms. So nothing has been created or destroyed. All we have done is rearranged the atoms into new compounds, going from methane gas and oxygen gas to carbon dioxide and water. And this is just burning natural gas, what might heat your home or heat the Bunsen burner. So we have law of conservation of mass in pictures. And we are going to do a demonstration class where we drop Alka-Seltzer in a closed system into water. And again, we are going to see the reactants and the products. And again, they're separated by this arrow. The reactants are sodium bicarbonate. This is the formula for sodium bicarbonate, the compound, plus citric acid. And this is the weird formula for citric acid, the compound. These little parentheses terms are talking about the phase, and we'll talk about that a little bit later. AQ just means it's in water, and L means liquid, and G means gas. So sodium bicarbonate, citric acid give us sodium citrate plus water plus carbon dioxide. And at the beginning, you'll see that the mass of the Alka-Seltzer and the citric acid stays the same as the products, as the mass afterwards. And so you'll see that demonstration if you're here in class. And that is it.